The VM Protect system is a revolutionary approach to obfuscation, designed to secure executables and malware through a custom C++ virtual machine. Its primary goal is to prevent reverse engineering by transforming original machine code into an unrecognizable format. Through a series of carefully crafted obfuscation techniques, this system hides the true nature of the executable, making it nearly impossible for anyone to analyze or extract the original logic. At the heart of this obfuscation is the use of unique proprietary instructions that mask the original functionality. These instructions are dynamically mapped into real machine operations at runtime, meaning that anyone attempting to reverse engineer the code will encounter a jumble of meaningless operations that disguise the executable's true intent. This method effectively complicates static and dynamic analysis, forcing analysts to deal with layers of confusion instead of the actual program flow. The VM Protect system goes beyond simple instruction-level obfuscation. It ensures that even if someone attempts to run the executable in a debugger or use a disassembler, the actual operations remain hidden. The custom virtual machine's behavior is unpredictable, making analysis incredibly time-consuming and virtually impossible to automate. This means that malicious executables or sensitive applications can be deployed with a much higher level of security, knowing that they are almost entirely resistant to reverse engineering techniques. Additionally, the system incorporates robust memory management. It allocates executable memory dynamically, ensuring that no residual data is left behind that could potentially be used for analysis. Each instruction is securely loaded and executed in real time, with no trace left in memory after execution, preventing code analysis tools from discovering the original content.
By using advanced techniques like multi-threading and synchronization, the VM Protect system also adds a layer of complexity to reverse engineering. Multiple threads work in parallel, each executing different parts of the obfuscated code, making it even harder to track execution and understand the inner workings of the malware or executable. In summary, the VM Protect system offers an unparalleled solution for obfuscating executables and malware, ensuring that reverse engineering attempts are thwarted at every turn. Through its unique combination of dynamic instruction mapping, memory management, and multi-threading, it provides an unmatched level of security that protects sensitive applications from being compromised or analyzed.
Code appraisal for polymorphic packer with AES-256 encryption, compression, and TUI interface overview. The provided code represents a polymorphic packer utility written in Rust, designed to read, compress, encrypt, and wrap a given executable into a polymorphic executable with AES-256 encryption using a CBC block mode. Additionally, it provides a text user interface, TUI, with real-time progress updates during the execution of the packing process. The packed executable is generated in a Rust-based project, ensuring polymorphism and hiding the original payload. This is a sophisticated and feature-rich implementation. Key features: AES-256, encryption with CBC mode. The encryption routine ensures that payloads are securely encrypted using a dynamic AES-256 key and IV, which adds a layer of complexity and security to the packed executable. The CBC block mode and PKCS7 padding are implemented correctly for secure encryption and decryption. Payload compression. The use of SLIB compression ensures that the packed payload is smaller, aiding in faster transmission and reducing the overall size of the packed executable. Polymorphism. The code dynamically generates a polymorphic stub using the encrypted payload. The stub is then compiled into a Rust-based executable using the cargo build system. This approach makes it harder for static analysis tools to detect the packed executable. TUI, Text User Interface. The use of a terminal-based user interface adds an interactive element to the packing process, allowing the user to track the progress of encryption and packing in real time. The UI is well organized, displaying status updates, progress bars, logs, and general information in separate sections, ensuring the user can follow the process intuitively. Error handling. The code does a good job of handling errors. It checks if the input file is a valid executable format, PE or ELF, and handles unsupported formats with appropriate feedback. The packing process is wrapped in a thread, and progress updates are sent through a channel, ensuring the UI remains responsive. Strengths. Security. The implementation of AES-256 encryption provides a high level of security. with dynamically generated keys and IVs, ensuring that each packing operation results in a unique packed executable. The use of CBC block mode and zlib compression ensures that the packed payload remains obfuscated and secure. Modularity and readability. The code is well organized with clear separation of concerns. Functions are small, focused, and handle a single responsibility, e.g., encryption, compression, generating the polymorphic stub. Rust's ownership and borrowing model is well utilized, ensuring memory safety and efficient handling of resources. Real-time user feedback. The interactive TUI is a fantastic addition, providing real-time progress updates, status messages, and logs, which improves the user experience. The layout is well thought out, with progress bars, logs, and system information clearly separated.